But we're gonna trust you.
I'm thinking 80,000 makes a little more sense, but,
So
That's just what I got.
multiply by 2.
okay, so this is QV,
I think I might.
right? So let's put some numbers in here and just see what we can do with this.
Wait, yeah, what question are we on? I'm lost.
Well,
We
how much
calculated
voltage do you need
Got
to
it.
create the radius or to bring it up to 5 centimeter exit point?
Got it.
So we've got mv squared over r should correspond to qvb, right? Or E, if you will. So we know everything but, let's see, so let's place this in different terms. That would be 2, my pen's dying on me, 2qv. Is this 2q delta v?
Yes.
Over qvb should be equal to r. Oh, I don't know, I'm not sure why I'm doing it that way, because I don't need any, I'm going the wrong direction, damn it. So 2q delta v over r, let's do it in 2 parts, qvb. And we want delta v. So delta v should correspond to qvb r divided by 2q. Yeah? So I don't know, there's a few different ways to approach this. I don't know if we can do it this way because we don't know what v is.
Yeah, you can just relate V to the other, because there's the relationship that QVB is equal to MV squared over R. You can solve for V and just replace that with the other variables.
And what we did before, when we were trying to figure out where the electron exited the field, we had R equals 4Q V over F.
I just canceled those Q's out.
Yeah, q's go away.
VB, and then I ended up doing 0.5 over 4, since you have
Okay, so
So
how do we
0.5
get,
is
how do we
too
get v then, or v, excuse me?
Well, V would have just been,
which V, velocity or voltage?
Velocity. We've got 2 unknowns in this equation right now, right?
Oh no, we have V.
We found V.
We found V with a kinetic energy.
Oh, you just went ahead and directly calculated it?
Yeah.
Okay, so, well, I guess we can just put that in here anyway, we just have to do the same substitution here.
RQV.
So v should go as a square root, so we end up with a bunch of crap that's gonna go around here. I'm gonna bring the v over here. No, it doesn't matter where we put it. So v is gonna go as 2q big V over m. And we've got v r over 2, something like that, then we just solve for delta v.
What's next to your M in that denominator there?
And that's mass of the electron.
Oh, okay.
Call it M.
Sorry. Yeah.
So I'm going to bring the square root of v over here. So we'll get rid of that. And so we should be left with, some of this stuff's going to go away. 2q er over 2.
Where'd the M go?
Right there.
It was there all along. I
It was
just didn't
there all
see it.
along. So we've got, this is the square root of delta v.
Okay.
So I'm doing my math all screwed. To get this, we basically got to square everything.
Right.
So what's that gonna do here? This becomes a
2Q.
4. This goes away. Squared, squared.
Looks a little nicer if you put the n in the denominator, right?
Sure does.
Take that 2 and
Okay, so how about that? There.
boom,
Boom.
bang, bang.
So you plug that into the calculation? Is that, have I done something
No,
screwy?
no, it's.
Good to this.
I don't think it's gonna be too much different.
Well, it should be the same number. So it's 1.6. I had to have something myself. In other words, I didn't have it in my head off the bat, so that's why I had to do the calculation. And I should have went upstairs and did it, but I was too busy drinking my coffee and enjoying,
Checking those Facebook.
checking out my Facebook, because I've got so many people just dying to talk to me.
Updating status.
And so we've got a radius of 0.05 squared.
Oh, no, 2.5.
There's a huge fall.
The distance.
Yes, we do. 5 squared. Wonder if that was it. And we divide this whole thing by 2 times 9.1, the negative 31. 3, 6. 4.9 times 10 to the 8th volts.
Yeah, that's what my calculator says here, but that is ridiculously huge.
Yeah.
Did that so much more simpler.
He ended up doing essentially the same thing.
Okay.
Yeah, that's a bit high, but
Is there do we make an error somewhere here?
well, dimensional analysis would tell us what? If we divided that by 3, that's still, no, it's all got to be squared there.
This is 1/2 mv squared. So this squared is 1/2.
So what's the velocity to go up that high?
mv squared.
It's a lot slower, right?
So yeah, since q equals W.
Well, I guess it doesn't really want to take that route, I suppose.
Oh, wait.
So let's take it, maybe a simpler tack. I don't know if there's a simpler tack, but let's try.
Right, so using this velocity over here
This square on the cube.
Okay, so FV,
is inappropriate.
oh, you can't use the same velocity.
Yeah.
It's
So
gonna
if we
be,
use FB, yeah,
No,
if we use
yeah.
FB, it's cool though.
so you get MV squared over R,
Yeah. And then,
and this is gonna be QVV. That right? So we can get rid of one of those V's, and so whatever V would need to be, it would be Q, B, R over M. That should be V. Yes, no?
Yeah.
What does this work out to be? Let's just start there. So I won't be deriving anymore, trying to get a simpler equation. Let's just plug numbers in here so that it'll keep me from thinking out loud. This was 3 Tesla, right?
Yeah.
Okay. And then we divide all of that by 9.1, negative 31. Okay, there's the problem right there. You can't solve that. That's faster than the speed of light.
Well, that explains why we had such a ridiculous
It would
voltage.
have to be,
You gave us a problem.
I know, I'm just saying.
just saying.
What's that?
I didn't convert them to Q and all that.
Is that really faster?
Because we did, in the last step, we did MV squared over R equals FB. Right, we put that down before. But then, when we solved for R, then we converted MV squared into 4 delta K, and then
Yeah, that's faster.
converted that to
4 delta K? MV squared is 2 delta. There might be something else in there. There's a 2 that comes up somewhere. But
Don't worry, it'll work.
It's a lot faster than the speed of light.
yeah, it's like 10 to the 10th. That's
Yeah, like 2 orders of magnitude larger than the speed of light.
That's possible.
Yeah.
yeah. You need a much smaller V to make this even
Oh, for the E-Cobra? Yeah.
be decent in any stretch.
That's still
Okay, feel free to delete that whole 20 minutes of discussion there.
So what happens there? You increase this potential difference by that much somehow, and then this thing just cannot physically move that fast.
Right.
So
It cannot physically move that fast because the energy is going to go, there's a relativistic calculation for energy.
but it can't move that fast, so you keep on increasing this voltage. That energy's got to go somewhere, right?
No, what's happening is the mass increases
Gotcha.
as it's going faster. I mean, there's the little extra something that's going on there, but the mass itself increases. So, okay, so that's not, those numbers,
So that doesn't work.
you should be able to use
What?
3 Tesla, the Tesla must just be way too high.
You're right.
Well, is it the Tesla that's way too high, or is it this R that we're trying to create?
Yeah.
No, they actually use devices where you take like 0.05 centimeters. So,
3 Tesla?
okay,
I mean,
10 to the negative 19th, it's, electrons are small, but you can deal with that. That's not the end of the world. That's, why is that? Okay,
Wait, exceeding.
I'm conceding it. But I will tell you that the relativistic mass, which is perceived, goes as the mass, the rest mass over the square root of 1 minus the actual speed over c squared. So, if you did the 1/2 mv squared to this, you can see that the whole thing kind of changes. So, plug that in there. That's the relativistic mass. This is what happens to electrons, by the way, when they try getting closer to the speed of light. As it goes faster and faster, the electrons increase in mass by orders of magnitude.
Is that related to MC squared?
MC squared comes out of this, actually. This itself is not related to MC squared, but if you monkey around with it, what you end up getting is MC squared plus a bunch of other energy terms. So it simplifies out of that if you fiddle around with it enough. But let's not. Okay, so wasn't that fun? Sorry about that. I knew I should. The way everything else is going today, I knew I shouldn't have did that.
going fine until you got that last extra question.
You know, yeah. Well,
Yes, what are you doing?
you know, these devices, let's make one change here.
Oh, here we go.
No, just one change. Let's just see.
Let's dig a deeper hole.
No. Let's just see.
What if?
Okay? If we replaced the electron with even just say a hydrogen ion. So instead of 9.1 times 10 to the 6th, or negative 31,
Right.
if you replace that with say 1.67 times 10 to the negative 27.
Okay.
Now you've got thousands different. So now you're back to this to 10 to the negative 6. That's the problem. You don't use these devices to measure electrons. You use these devices to measure charged ions. See, so I'm just not thinking.
Okay, we're
What
back
is it,
around.
1.67?
Times 10 to the negative 27.
I just,
Okay, I got.
I just got this
the
number and I'm
voltage
like,
I
what
got
the
is,
Okay, well, all you have to do is take this number. What's that horrible number we just had?
So,
Was that 1.3 times 10 to the 10th or something like that?
yeah, but
So-
now we've got something that is,
now we're at, below the speed of light.
yeah.
Okay, so you
7.19
take
times
this number,
10 to the
yes,
6.
that's,
Hey, there we go.
Hey.
We're not breaking laws of physics now.
correct.
Very good.
Well, I 3.6. Yeah, now we're at like 7 million meters per second. Actually, that makes a lot more sense. Okay, so here's the moral of the story, what I was going to point out earlier. They actually use this type of a device, it's called a mass spectrometer, to measure the mass of ions. It just dawned on me, you would never run an electron through that, right? You'd use an because of the voltages that would be required to get an electron to expand into that circle.
So for an electron, you would use a smaller radius or something?
You'd use a smaller radius or a much lower beat.
How many orders?
So this whole model was how a mass spectrometer works,
It was if you plug another number in here. So,
but that physically they have something go into a little hole and then they measure where it comes back out of the magnetic field.
yeah. And what you do is you fine tune either the voltage in a constant magnetic field, or more often than not, you have it like a set 1500 volts, and you fine tune the magnetic field until it comes out. And so you're sitting there doing this until the detector reads something. And when the detector reads it, you go, okay, I know what it, now that corresponds to some mass. What is it? Doesn't tell you what it is, but it tells you what the mass is.
That's pretty cool.
Yeah, so think about some organic compound that's got like 6 carbons, a bunch of hydrogens, some oxygens, and nitrogens. And you get some mass that's like 1,000 times this, or say 50 times this. And then you just start using common denominators, or you start looking at known masses of chemical toxins or common compounds and just try to see what it's likely to be. So that was essentially what I was getting at. It was, best laid plans. Don't always work, right? Certainly not when it's my Monday, that's what it is. It's my Monday. And yours too. Okay, so let's change this and look at current carrying wires. We'll come back to that whole mass spectrometer thing. In fact, it's in the worksheet. There are worksheet problems related to that. So I got egg on my face here, but regardless, we'll just deal with it.
That's going to be an exam.
Okay, so the idea is essentially this. When you have a current in a wire, rather than a charge moving through space, so this is our wire, and it's got a current running through it, which means electrons are running backwards. And maybe we have a magnetic field, start out with it being constant, something like this. So we've got a 90-degree angle between the B field and the movement of the charge. The magnetic force is related to the magnitude of the current passing through the wire. times the length of the wire, cross product or cross multiplied with the magnetic field. So again, in practice, what this means is that the magnetic force is perpendicular to the direction of the wire, which is the direction the current is flowing, and the magnetic field. So, fingers in the direction of the wire in this case, curl my hand. Oh, crap. Oh, there we go. Wire, curling. Oh, it's upside down.
Yeah.
Upside down. I gotta flip it.
There we go.
Flip it. This way, this way. There we go. There we go. Got it. Got it. Got it. There we go. The magnetic force would be coming out like this.
Are you sure?
I'm sure. Okay, so the magnetic force then would be coming out like this. Again, 90-degree angle to everything involved.
Yeah.
This is one of the pleasures at the end of any given year that physics instructors have is having their students have to apply the right-hand rule
That's terrible.
for something that doesn't fit on a nice, even.
Yeah.
Okay, so we got all of these
It's all right.
right angles, right?
Oh, we don't have
It almost works if you stand and stare at it. That's rare for me. That almost worked.
Wow.
Okay. Or, if you will, the force per unit length, the magnitude of force per unit length goes as IB times the sine of the angle between the L and B. And the angle is based on the right-hand rule. So rather than trying to calculate it, you just do that. And then you do it this way. I don't know what rule that is, but you know. Normal force.
That's a cross.
Right? Okay.
What's a magnetic field resistor?
Now, I pointed out this way because if you don't necessarily have a particular length in question, the force per unit length is related to this stuff. But the direction would still be according to the right-hand rule. So if you knew you had 1 meter of length, then you could deal with it, of this wire in this magnetic field. If you don't, you can still calculate the force per unit length. So, pretty straightforward. There's not too much to it, other than applying our good friend the right-hand rule.
Yeah, I don't know about that.
I don't know. Yeah.
So-
This friendship is a love hate.
It is a left hand.
When we talk about
There are a lot better things to do with your right hand, I know. But it's just, there you go.
when we talk about an electric field,
It almost works, doesn't it, to you with it?
then
He's like, nope.
Look, Ma, it's three-dimensional. Okay, go ahead.
when we're talking about an electric field, our electric force gets to be in the direction of the electric field. But when we talk about a magnetic field, it's perpendicular to this magnetic field.
When the charge is moving,
Okay, when the charge isn't moving, then you don't have anything, right? So, why? Why would we want to? So, okay, we got.
oh, okay, let me see if I can phrase it in one sentence.
Oh, wow.
Because one man's electric field, or no, let me say the lazy man's electric field is the running man's magnetic field. Moving charge, you see a magnetic field. When you have two moving charges relative to each other, then the interaction by charge is perpendicular, and that's our magnetic field.
So a lazy man is a magnetic field that just sits there and watches the.
No, that's the charge. That's just the charge. It's not the stationary charges that are not moving at all. So you're watching a charge, you see nothing. But if you're moving with respect to the charge, you see a magnetic field.
You see it.
So if you had a moving charge in your reference frame as you moved by a stationary to the ground electric charge, the interaction between them would look perpendicular. So there's really three things involved. There's the moving charge that produces the field. There's the moving charge relative to the observer that sees that interacts with that moving charge. And then the magnetic field is produced or observed by the person who's watching both simultaneously.
All right. I'll
Okay.
think about that one first.
Okay, so here you go. Let's put it in context. So we've got a scientist on a bus,
Is he
and he
positively
sees
charged?
a stationary, and that bus is moving at some velocity. So he sees a stationary charge relative to the ground. With respect to him, the charge appears to be moving this direction.
Right.
Okay? So, if he were then to simultaneously take his pet electron and toss it up into the air, that's Q naught and Q1, the interaction that he would see would be a magnetic one. If the charge is going by and he just holds the electron or the charge in his reference frame, he wouldn't see anything because the charge is stationary to him. So it's a stationary charge in the presence of a magnetic field, nothing. So it requires that you have a charge that's moving relative to both the observer and the source charge. And when you vector it out and look at it very carefully, you need to calculate what this moving charge is. What you end up getting is a perpendicular electric force, if you will, that we correspond to the magnetic, which is why they call it electromagnetic interaction, because they're really one and the same depending on how you're looking at it.
So this thing that we set up here with our wire, I thought that as soon as we put a current through that wire, that it would create its own magnetic field in circles around the wire.
It does. But that magnetic field doesn't interact with itself. It interacts with another moving charge independent of it.
Which is this other green magnetic field that we set up.
Yes, so the question is, now we'll back it up here, what is it that produces the external magnetic field? So this current here, in fact, produces its own magnetic field. We've seen it. But when you take that current and put it in another magnetic field, what is it that produces this magnetic field? Well, it could be a bar magnet, or it could even be another wire. It doesn't matter. The bottom line is, when you have a magnetic field relative to this that's not its own, then you'll have an observed associated magnetic force. So you got to be careful because you got different players. It's not self-magnetism that's affecting itself. It's something that's exerted on something else altogether. So this is a crazy thing, though, because if you're moving with that second charge, you're moving with it. You don't see a magnetic field because you're moving with the charge. You have to be stationary to the charge that you're observing in the presence of some other magnetic field. Because velocity is relative. This is part of the reason why Newton's laws sort of broke down and Einstein had to reinterpret them. The other is that the interaction is limited by the speed of light in general. We got all kinds of stuff going on here. And nobody's doing an Einstein paper this quarter, so we don't have a way of backfilling it. And, we're not going to have time. What's that?
We're doing.
Oh, okay. We have someone doing it. So we got different things going on here. The question is, you got to look for the holes in the logic, if you will. Now, for us though, this is essentially what we're concerned with. Okay, so if we take that same 3 Tesla magnetic field and run a current of 1 ampere. The force per unit length would be the 1 ampere times the 3 Tesla 90 degrees, so I'm gonna ignore this part. There's nothing else to divide or multiply. It would just be 3 newtons per meter. So if the wire had a length, say 0.5 meters, then the magnetic force on that segment of wire would be 3 newtons per meter times 0.5. So it's, now, I'm getting ready to go here, but I'm gonna throw one little bit at you to just kind of keep in mind. Always, right? That's circular, the magnetic field created by a wire. Yeah, I think I gave this, didn't I? On Thursday. A straight wire produces
Maybe Friday, I think it's the first time we talked
the,
about that.
yeah, I thought we talked ever so slightly about it and didn't put much to it. But for this particular wire, for instance, the magnetic field associated with the wire goes as mu naught I over 2 pi r, where r is the distance of separation. So here's your current. The orientation is 90 degrees, but if you're at some distance r away, the magnetic field up here at this distance would be inversely related to how far away you are. And the magnetic field would curl, according to the right-hand rule, thumb in the direction of the current. So the field would curl something like this. Out of the board, into the board. I can't draw that, so I'll leave it at that.
The magnetic force is in the direction of the current? Is that,
Not magnetic force, the magnetic field.
well, it's perpendicular to the current.
Yes.
But the magnetic force then on,
This is not creating a field on itself, again, remember? This is the field produced by this wire.
okay, so.
So if I
thinking about
had
backwards
another
then.
wire over here, and the current were pointing in some direction, now you have I pointing this way, but you have a field going in. What does that give us? Down. Like this. They push away from each other.
Okay, so then thinking about this sort of backwards, but like a